maybe what I'll do is just remind us of the recap from last time. So let me bring that up. Wasn't sure exactly what format we would take here. So let's try this. Okay, so these are just the slides from part 3. And again, I just want to make a reminder that all these slides are available online. I believe they've already been shared with you, but also they're up on my webpage. So just a reminder, we've been studying variational Bayes this whole time. I think with any method that you learn about in machine learning, you want to learn, how it works, what's the mechanism, when it works well, and what are the potential issues with it. Every method has potential issues, and so it's best that you know them rather than be caught unawares by them. So we've been looking at variational Bayes. The real motivation that we've seen this whole time is that we want to do Bayesian inference. We have, all these very exciting applications. This is really just the tip of the iceberg in terms of applications. I think if you just think about any major area in science or, major sort of breakthroughs in science or technology or engineering or social sciences, these days it seems like Bayesian inference is everywhere. And so an issue that practitioners often find themselves facing is how to get really fast Bayesian inference. And so certainly, one of the things we talked about was COVID-19. Here we're clearly in a situation where we want to be getting insights as quickly as possible. We don't want the machine learning to be the holdup for people. And I want to emphasize that, again, there are 2 aspects to speed. So one is compute time. We don't want to have to wait around a month for something to run, especially if we find out there's a bug after a month and then we have to iterate and so on. But also there's user time. So there's been this really, I think, super important focus in the Bayesian community on making really easy to use functional, methods. So like these probabilistic programming languages that are really easy to use and super practical, and that let you just put in essentially a super broad range of models, whatever new model you come up with, and that you can get a nice, approximate posterior out. And so that's the kind of thing we're looking for. We're looking for something that's going to work really generally for a really broad range of models. Because if you have to sit down, and you're in a different area like physics or chemistry or the social sciences or biology or what have you, and you have to sit down for weeks or months and derive equations to get a method to work or create a whole new method, maybe together with some machine learning experts, that's going to really slow you down. And so it'd be really nice to have something that just works really automatically for this wide range of models and a new model that comes up that we've never seen before. And so that's what we're thinking about in terms of user time. And so there's been a lot of really great work on this. But an issue that seems to arise to this day, and so I think this is some interesting, exciting work to be done here, is that it's hard to get speed at the same time as accuracy. So there are methods that can be very accurate, that have a lot of diagnostics associated with them, that have a lot of theoretical guarantees associated with them, but might be quite slow in practice, especially on maybe larger data sets and things like that. And then conversely, there are methods that can be extremely fast. We even talked about things like map, just using map, but might not be as reliable, at least for the purposes that we've been discussing here. And I think something also, like as a meta point, that's really important whenever you're discussing machine learning, is to make your goalposts clear when you're starting. What is the goal? Because there are so many different types of things that we're trying to do in machine learning. Prediction, making sense of data, understanding some unknown parameter. And so here, throughout this talk, our goalpost has been, we want to do something like parameter estimation. There's some unknown in our models, and we want to estimate it. And in particular, we're going to look for a posterior mean and a posterior variance as our notion of what's our best guess of the value of this unknown parameter and what's our uncertainty of that value. And so for those goalposts, we've really been examining, variational Bayes. Does it help us? Is this a useful tool in our toolbox? And we spent a lot of time going through this. And again, this Criteo example is just one of the many examples that we spent some time on. But something that we saw in this example is that we can get these really good point estimates. I mean, I think surprisingly good that this is such a complex model, and we make this very strong mean field assumption. And yet still, we see that the mean field variational Bayes point estimates agree with this Markov-Chain Monte Carlo, standard method that's in some sense sort of state of the art in terms of accuracy. And so we get this really nice check. And of course, there was this issue with standard deviations. And we saw that it wasn't just an issue of like, oh, maybe there's a bug in my code and that's why we're seeing these issues. No, it's really fundamental because we can see this even in theoretical cases where we know the exact mean field variational Bayes optimum. And so we know this isn't just a bug, this is a real thing that happens with mean field variational Bayes. And we saw that, in fact, this kind of motif happens in a lot of other areas, and that it's really not even just the standard deviations that can be wrong. In fact, the posterior means can be wrong as well, although that seems to be less common in practice. It can happen. And I think the real challenge in all of this is that you don't know if it's happened or not a priori. You got an answer back, but you don't know the ground truth. And so how do you know if you can trust that or not? And so last time we spent a lot of time thinking about, not just what's the nature of this problem, where does it arise? We saw that there were, some implications of mean field variational Bayes, but also the Kale divergence itself had some issues, some potential issues, at least in practical realms, where we're not exactly getting it to zero. And then we spent some time thinking about some solutions. It turns out this uncertainty thing is actually not at the root of the problem. If we could get the means just right, the uncertainties are not a problem because we can use linear response variational Bayes and get at least accurate covariances. And then we spent some time talking about, okay, but means, what do you do about the means? And explored some potential options. So one is to find a method that actually does have theoretical guarantees associated with it. Things like core sets, getting at the core of the data set can do that. And I think there's a lot of other interesting ideas that we can think about. But in general, this idea of data summarization as a pre-processing step before you run an algorithm that is expensive in data is a really interesting idea. And I think it's, it's a very hot sort of area right now. Separately, we also talked about, well, maybe we just want to do what we're doing right now. It's fast, sometimes it works, and then we want to check after the fact. So did it work? That's the kind of question that we're asking. And so we've been doing some work, and I think a number of awesome people have been doing work on basically figuring out ways to check, to do an after the fact check on what we're doing. So we propose having a check that lets you actually have a guarantee on Wasserstein distance, which in fact lets you have a guarantee on how close you are in your posterior mean, how close you are in your posterior variance, the things that we have purported to care about in this talk. And then I think, also one of the things we've been focusing on is having a really clear workflow, something that could be part of black box variational inference, where black box here means something different than you might see in other areas of machine learning. Black box means that the user doesn't have to be super involved with, deriving the variational optimization objective, with figuring out how to optimize it, or in the case of MCMC, that basically they don't have to be involved with approximating the posterior, that we're going to do that for them. And so that's it's a different kind of thing, because here it's really important that the user is involved with choosing a model, because that's one of the main things that we want them to be involved with, that we want to say, what is the relationship between the parameter and the data? What are you trying to learn out of this problem for interpretability reasons, to incorporate their expert information, and so on. And so anyway, so this is something that we've been working on, not just validating variational inference, but having a validated workflow. And I think there's this great paper by Yao et al. That I mentioned last time, and I think its title just sums up our goal in this kind of post hoc check, which is it's called Yes, but Did It Work? And it's something like checking if variational inference worked, and it's just a really fantastic title, and I think it gets at the heart of this question of, yes, you ran something in machine learning, but did that thing work? And I think that's a question we have to ask ourselves with any algorithm that we're running. Yes, but did it work? You got a number out. What does that number mean, and can you trust it? And I think that's just, again, always a question you should be asking with any method. And if you don't have a great answer, then maybe it deserves digging a little bit deeper into that method. Okay, hopefully that's a reasonable overview. But of course, if anybody has just general clarifying questions, or wants me to go back on something that we covered, I'm super happy to do that as well, if that would be helpful.
Great. So taking from that point, if someone wants to start doing Bayesian inference, so variational inference and so on, where should one start? What would you say the person needs as background, as starting point?
Yeah, so I think there are different types of things one could be looking to do in Bayesian inference. So if you're just looking to apply Bayesian inference and you're looking to use it for your applications, then I'm going to mention some tools and some resources. So there's this nice Bayesian data analysis book by Andrew Gelman that sort of goes through, here's some common things that you might do with a Bayesian model. Peter Hoff also has a really nice textbook that's sort of like, oh, let's get an introduction to the types of modeling you would do, because the real first question in Bayesian inference, and one that we did not cover here, as I emphasized in the beginning, is choosing a model. And so if you're actually going to use Bayesian inference in practice, the first thing you need to know how to do is to choose your likelihood and to choose your prior. And there are some cases where if you're doing a certain type of problem, like topic modeling, there's a really clear choice. Or if you just want to understand how some features relate to a response, then various types of linear modeling make sense. But beyond that, I think you have to start understanding what are the available options, what would make sense, what are usual and useful choices of likelihoods and priors. And so from that perspective, I think those textbooks are quite good. Also, I think Chris Bishop's Pattern Recognition and Machine Learning is just an excellent textbook. Kevin Murphy's Probabilistic Machine Learning is also an excellent textbook. I mean, honestly, there's some really great resources out here, and many of them are totally free online, which I think is really great. So, Chris Bishop's book is totally free online. A lot of these are free online. Also, David Mackay has a nice textbook, which is a bit older now, but has not lost any of its applicability. Okay, so these are some resources to start learning about, what are these models? What am I doing? And I think one thing that's really nice about Bayesian data analysis is it's really grounded in some very concrete examples, because Andrew Gelman has very famously worked on some very concrete uses of Bayesian inference. Okay, so now how are you going to do your Bayesian inference? Now, if you are a practitioner, like if you're not looking to innovate in the space of approximate Bayesian inference, or if you are somebody who's looking to innovate, but you just want to run some stuff to get a feel for what's going on, I super strongly recommend that you do not derive and code these algorithms yourself. Even if you are like the best person at math and coding and everything, just we all make bugs. It's unavoidable. And there's been just a huge amount, like so much human hours of engineering that have gone into these excellent probabilistic programming packages now that like there's no reason. Like you should definitely be running those. And if you're even doing innovative, approximate Bayesian inference research, you should be comparing to those. And so I want to, in particular, mention a couple. So there's Stan is just a huge one in this area. It's been downloaded millions of times. It's hugely useful. And there are two things that are worth noting: that Stan has both Markov-Chain Monte Carlo, in fact, sort of this state-of-the-art Markov-Chain Monte Carlo, which is this version of Hamiltonian Monte Carlo. So Hamiltonian Monte Carlo has sort of this interesting history that, it's been around for a really long time, and Radford Neal did all this amazing work on it. And people weren't using it so much, in part because it had these hyperparameters that needed to be tuned. And so then there was this excellent no Uturn Sampler paper that really made it something that could be automated. I mean, it's hard to do on your own. You don't want to code it on your own, but it's something that once you put it into a probabilistic programming language can be, very easy for somebody to use. And so now they have that. Now, there are other probabilistic programming languages that I highly recommend looking at because they're sort of competing in this space, and especially in variational inference. So you get things like Pyro and PyMC3, and I think that it's worth trying them both, especially if you're running into any issues, because then you can see sort of, oh, some have different strengths in different areas. And TensorFlow has really awesome development. And so basically, the strongest recommendation though is that you be using these existing probabilistic programming languages rather than coding things up yourself, especially to begin, because it's just going to be a huge waste of time otherwise. And I think this is the way to go. I see there's a question in the chat about if MCMC is too expensive, We can do gradient-based MCMC like Mahler. We can do approximate posterior by VB. So there's a choice to be made. How do we make this choice? I think this is an excellent question. You know, how do we choose whether to use MCMC or VB? I'm going to give you some personal thoughts about this, and I think it may vary by practitioner. So maybe, you know, ask your friends as well. I think what you find nowadays is that there's a really clear divide in terms of how people are using variational Bayes in practice versus how they're using Markov-Chain Monte Carlo. So something we did not spend time in this tutorial talking about is this issue of multimodality. What if you have a multimodal posterior? What happens there? Now, I think there are at least 3 types of multimodality. So one is you have multiple modes in your posterior, and there's a relatively small number of them, and you actually care about those modes and you really want to approximate them. First of all, you probably shouldn't be using a posterior mean and a variance to encode what you know about your posterior there, because really you want to be saying that, like, hey, there's this small number of things that are going on, and so you want to think about other summaries. So let's put that to the side for the moment. Now there's another type of multimodality, and this is a tricky one that comes up in things like clustering or topic modeling. So if you're doing clustering, what's typically happening is that you get a mode for, you know, this is cluster number 1, and this is cluster number 2, and this is cluster number 3. But, you know, you just had to encode it in your computer somehow. This could have been cluster number 1, and this could have been cluster number 2, and this could have been cluster number 3. Like, you could have rearranged the order of those. And it's the exact same clustering. It's just encoded in your computer slightly differently. And so actually a big strength of variational Bayes is that, especially mean field variational Bayes, really mean field variational Bayes, is that it has a tendency to pick out a single node. I say tendency because it doesn't have to, but it does have that tendency, and that can be really useful for something like clustering or topic modeling, where you're doing unsupervised learning, and you don't want to average over all of these modes that are actually just completely equivalent if you were working in the space that you really wanted to, which is this sort of equivalent space. And so MCMC really struggles in these problems due to an issue known as label switching, whereas VB does not, because it just picks out a single mode. So there are cases that, like that first case I mentioned, where you have a bunch of modes, you really care about them, and then you might worry about mean field variational Bayes picking out a single mode. But in this case, in like clustering and topic modeling, this could be really desirable. And then there's a third type of multimodality, which is where you have a ton of modes and you don't really know what you want to do with them. And I'm not going to get into that, but like I want to say a first thing, which is that like multimodality is not a single thing. Like there are a lot of things that you might want to do within a multimodal space. But because there is this one type of multimodality that comes up in basically unsupervised learning, I think this has been an area that variational Bayes has really shown, and that we really see it used a lot. And I think it's not a coincidence that this is a case where we see that people don't exactly care about the exact posterior mean or the exact posterior uncertainty. This is a case where they want to get a sense of what's going on in the data. And then you can get like these nice things that you get out of some forms of probabilistic learning, like regularization and, you know, the ability to explore the space a little bit easier, and just, you know, being able to build a model really easily with this generative models framework. And so I think this is my feeling, perhaps, for why variational Bayes is so widely used for things like topic modeling and unsupervised learning and extensions of that, is that it's just this perfect confluence of all the strengths of variational Bayes. It's picking out certain modes. It's allowing you to run on the humongous data sets that you get in topic modeling, where you just have tons of data, or, you know, or modern networks where you have like all of the Twitter data or all of Facebook data or transportation network or something. So you get the speed, you don't care exactly about these exact posterior means and uncertainties, and you get this ability to pick out single modes. So that seems like a case where I would tend to use variational Bayes, because it's just going to, you know, get you the sort of useful things that you want. And then conversely, if we're in a lot of sort of scientific and engineering problems where you might not even have so much data that this issue even comes up, the speed issue, and you really, really care about getting your posterior mean right and your posterior variance right, and, you know, really encapsulating these things and saying very carefully what you get is your uncertainty, and you really care about getting that Bayesian estimation, I think this would be a case where people would tend to use MCMC. And so in a lot of these supervised learning problems, a lot of problems in sort of science and engineering and the social sciences where you care about these things, there's going to be a tendency to use MCMC. Now there's this awkward place in between, and I think this is where the real questions lie, is what if you have a case where you really care about your posterior means and variances, you do want to get them right, but you have so much data that MCMC becomes impossible. And so I think that's a case where, like, yeah, you kind of have to use VB right now because, you know, if you just can't run MCMC, you can't run it. But it would be nice to be able to do something where we can, you know, rely on our uncertainties, we can rely on our means, and we can, you know, get these useful quantities out. And I think that's an interesting space, in the space that some of these things are addressing, or even just quicker, you know, iteration, like you know, in this example that we're seeing here with the Criteo data, remember the actual data set is something like millions or billions. And so what's happening in this data set is we were only looking at a subset, 60,000, to be able to run MCMC, and it still took 6 hours. And so if I were iterating on my code, I wouldn't want to wait 6 hours to iterate. I'd much rather wait a minute. And so I think that's another case where BB could be a good thing to use. So I guess like a really big meta point here again is there's a lot of nuance. It, you know, depends on the problem, it depends on what you're doing, but I think these are all really useful tools in a toolbox. And I also think there's a lot of space for more development. Okay, I see there are a couple of other questions. Let me take a look here. So when using these frameworks such as STAN, do they automatically choose the class of proxy distributions in variational Bayes? Would one be restricted which models to use with BB? Okay, so this is a great question. So when you're looking at, so I'm going to focus on the variational Bayes part of the question. But well, actually, let me just address this broadly. So if you're looking at something like Markov chain Monte Carlo, because that's also something that they do, that these probabilistic programming languages do, there are some restrictions, although in you know, they are on the model itself, and this is an important distinction that we made earlier when we were talking. Namely, and this is a thing that came up really earlier in our discussions, because they do something that involves automatic differentiation, and in particular, the way that Hamiltonian Monte Carlo works is that it sort of creates this, you know, this sort of space, which is, it's like you take your distribution and turn it upside down and then roll a ball in it. And so you have to have this sort of smoothness and this ability to take derivatives. And so that can be limiting, that you're not going to have, you know, things like discrete parameters because you can't roll a ball in a discrete parameter. And so that is a potential limitation. That's also a limitation that, again, coincidentally or not, affects things like clustering and topic modeling, and another reason that it's sort of easier to do those with variational Bayes. But an issue, so if we now focus on the variational Bayes side, what are the limitations there? If you look at probably the most popular form of variational Bayes in probabilistic programming languages, because it's so black box and so easy to use, it's what's known as automatic differentiation variational inference. And it essentially assumes not just, you know, that you're using some kind of exponential family as your approximation, but that you're using a Gaussian. Now, it might be in a transformed space, but it's still fundamentally a Gaussian, and that's going to make assumptions, assumptions that aren't always, you know, necessarily going to give you the absolute best approximation. And so it's something to be aware of, that typically that's going to be the class of proxy distributions. Again, possibly subject to transformations, but it'll essentially be something like a Gaussian proxy distribution, unless you know you're working in some other framework, but that would be the default one that you'll see in a lot of these languages. And so that part doesn't a priori restrict your models, although it has to be something that's on a continuous distribution again. So it's restricted in the way that it is for HMC, but it's not really restricting beyond that. You can use sort of any model that has, you know, parameter in a continuous range, but it's restricting your approximation class, and more so than what we've already seen here. And so that can, you know, add extra potential error, and something worth looking at. That being said, I will say that it really often looks like what we're seeing in this slide that we're sort of stopping on, which is that the means often look very good, the posterior means in practice. And I think it's sort of tricky because you don't know going in. Like, it's like, okay, if it looks really good in practice, that's good. Like, a lot of the time it's good, but what about the time it isn't? You know, and so on one hand, it's really exciting that it looks so good. You know, you feel like you can use this. On the other hand, you know, I think there's still more to be understood here about when that is, and can we reliably know that, either with a priori guarantees or post hoc checks. So I work on turbulent flows. Somebody says, so MCMC is very expensive for forward solve. Yeah, I mean, I think, as you know, especially as we get into these problems that aren't maybe sort of traditional generative models, are the ones that I feel like there's certain types of generative models that are just studied very widely. So things like generalized linear models, generalized linear mixed models, and then things like clustering and topic modeling, especially on the VB side, and then like variants on those. And so you see that like a lot of the research in this area is really focused on that. But of course, there's certainly, you know, other problems that really get beyond that. And you do find, I think that, you know, if you get into a class of problems that comes up again and again in an area, they can be really useful to develop some specialized tools for that, to have, you know, a class of models that's really useful, a class of inference algorithms that's really useful. So I don't want to suggest that like everybody in the world can and should be using these probabilistic programming languages with the default, you know, methods that are in them. You know, that you should just use, you know, HMC with nuts immediately, and you should use automatic differentiation variational Bayes immediately. You know, for some of these problems, you really can benefit from specialized tools, and I think that's why they exist and why they're so widespread. But you know, there's always a trade-off, right? So if you're just somebody new coming along and you have a problem that's kind of reminiscent of some of these existing ones, then this might be the fastest thing to do. And certainly that is the case with many of the examples we saw in the beginning of this talk. And, you know, I sort of mentioned these illustrative examples in Bayesian inference. But there are whole fields, like I think astro is a great example of this, astronomy and astrostatistics and in general, where there's just a lot of work on developing some sort of like specialized MCMC methods, because they really do have a certain flavor of a problem that can benefit from that. Okay, I think I went through everything that's in the text.
Yes, and I have many more questions from Slido. So
Okay.
Often the argument for using Bayes and investing in Bayesian methods, it is to estimate the uncertainty. And however, we can just do ensembles, deep ensembles, and this can be faster and also produce good results. So what would be your argument to advocate for using variational Bayes?
Yeah, so I think what's important to keep in mind is that there are different types of uncertainty. You might think of them as things like Bayesian uncertainty and frequentist uncertainty. And so with something like, you know, if you're doing something like the bootstrap, what you're getting at there is, if I change my data, like if there's some, you know, data generating process that creates multiple universes, and in every universe I got slightly different data under this data generating process, I'd like to be able to say, you know, am I pretty certain that I'm going to get the right parameter? Like this, suppose that there's some correct parameter that's generating all of this, and I want to estimate it. And so this is a traditional notion of frequentist uncertainty, and it's an important notion of uncertainty. And it's a really meaningful notion of uncertainty. I want to kind of say, like, I've developed this algorithm, and I want to make sure that it works, you know, most of the time, for some notion of most of the time. Now, conversely, what's sort of missing from that is this idea that there are things that I just don't know, right? So like, I don't have access to multiple universes for looking at the galaxies in the universe. I have the galaxies that I have, and I'm doing some kind of, you know, often doing some kind of statistical analyses of those galaxies. And so I want to encode that there's information that I don't quite have, that I have a degree of belief about that. And Bayesian inference is letting me do that. It's letting me get at that type of uncertainty, the lack of knowledge, something that isn't just purely about, like, you know, data changing under some perfect notion. I mean, this is the classic idea of what's random. Is it our data? You know, the frequentist sort of way of thinking about things is that our data is random, and that we want to say that under all the different data sets that we could have gotten, that we're going to do something good, that like our program is going to work, our algorithm is going to work, or at least with high probability. And then the Bayesian conversely says, well, I got the data I did. I mean, that's the only data there is, so it's not random. Whereas it's useful to think of my parameter as random, because I don't know about it, and I want to express that lack of knowledge in some coherent way, some way that, you know, has a variety of nice theoretical properties, like it's, you know, people aren't just going to beat me in bets and things like that. And so a Bayesian framework works for that. I think the reality is there isn't a right framework. I think these are both really useful ways of thinking about uncertainty, and they're both types of uncertainty that we should care about. And so, you know, I think you can get yourself into real limitations by not considering one or the other. The reality is you get a particular Bayesian mean for the data that you have, but it might be that your model is misspecified. And so, and every model is misspecified. We know this. There's this like really overused because it's such a good quote by George Box, which is, all models are wrong, but some are useful. So we know that our models are misspecified. And because they're misspecified, we know that our Bayesian uncertainty isn't going to be sort of exactly the type of uncertainty that we want to get. It's going to be an uncertainty for that model, for the data that we have, but because that model is wrong, it's going to miss some types of uncertainty. And so I have some really cool work, I think, coming out with my postdoc, Brian Giordano, on adding frequentist uncertainty to that mix and making this something that you can do really fast and easily. Hopefully that'll be up on the archive soon. But I think it's a general idea that isn't new to this work, that you can have both of these. I mean, you could always do bootstrap with this. And there's like this very nice paper by Jonathan Huggins and Jeff Miller that goes into that a bit. It's just, the only problem with that is that it's very expensive to run bootstrap because you have to run your method again and again. But I think the idea there is a great idea. And if you can run it, that's awesome. And then conversely, you don't want just frequentist uncertainty. There are these really sort of toy examples where you can imagine, like, I just happen to maybe only get data for people. I did a poll and I only got data for people who don't have a particular maybe medical condition, but I really want to include the people who have a medical condition. And I wouldn't want to just say by resampling my data that I had gotten all the different types of things that could be going on in that data, because I missed something about the data. And so what's nice about Bayesian methods is that they include that possibility that there's something you've missed, that there's something that isn't in your data, that there's some just notion of something that you haven't seen. Maybe I'll ask, should I just be going off your Slido questions, or should I be answering the ones that here? I'm happy to go with whatever way.
Well, I can be telling you the answers that come. So I have this one on, is KL divergence the only example of F divergence for which variational methods can be applied efficiently? No problems with normalization constant?
Okay, well, so we want to be careful here. So there are plenty of divergences for which some notion of this optimization problem that we set up can be applied and has been applied. So there's the chi-squared divergence, there's all the alpha divergences, F divergences. Like if you think of something, there's probably a paper on it that's out there. I guess what I wanted to convey in this part of the talk, where we talked about this nice thing where the normalizing constant pops out of the KL divergence, which is, I want to say, not just specifically a nice thing about the KL divergence, but specifically a nice thing about the KL divergence in that direction. So it's not as easy in the other direction. You don't just get that this pops out. It's just that that's convenient, because we want to ask. It's not just a question of what can be applied, but what's dominant. When you look at the way that people are using variational Bayes, yes, there's papers in all these different divergences, but you see that in practice, it seems like KL in this particular direction, that is typically called variational Bayes, is what's dominant, is what we see applied so widely, is what we see applied in so many different areas. And so we can ask ourselves, why is that? Why is this particular divergence among divergences applied so widely? Why is this particular divergence among distances? There are actual distances out there applied so widely, and I think some of this is convenience. I think this is an answer that may be unsatisfying sometimes to people, but I think is the reality of the world that we live in. Is that sometimes we don't do things because they're exactly the perfect thing. We don't do things because they're the only thing we can do. Sometimes we do things because they are convenient, and I think it's worth recognizing that, because it happens a lot in machine learning, more than maybe paper texts will let on their own. But I think this is a case where KL has this convenience. It makes it easy to do. And if you look at the early papers in variational Bayes, they're very much taking advantage of this. You're able to, now we talk about things like automatic differentiation, variational inference, where you're able to do these things in this very black box way that, the computer can just automatically figure out what's sort of the objective function, and then how do we optimize it. But in the early papers, people had to derive these by hand. And that's what you saw people doing, or at least they had to do that for a specific type of model, like these conditionally conjugate models. And KL was so convenient for that. And even now, you look at automatic differentiation, variational inference, and it uses the convenience of KL in it. So this is certainly not to say that you can't do things with other divergences. You absolutely can, and people have. But KL is particularly convenient, and I think it's always worth asking, why do we see a particular, dominant form of a method? And sometimes the answer is, convenience.
And do you believe in boosting the approximation of the posterior distribution based on simple Gaussian components? Is this better than standard variational approach?
I'm sorry, can you repeat the question?
So what about boosting the approximation of the posterior distribution?
I see. Yeah. Okay. So I think what this question is getting at is, so we talked about mean field variational Bayes. So remember, in variational Bayes, we had a collection of choices. In fact, I think this is, let's see if I have this as a slide coming up here. Yes, okay, so we made all of these choices, right? And so we made an optimization, we made the choice to make an optimization problem, and then we chose to minimize KL. And then the next choice is to say, what is a nice distribution? And so one of the things that we talked about, the thing that we really focused on was this mean field assumption. This idea that what you can do is you can factorize your distribution, so you effectively get sort of low dimensional parameters and distributions that you're learning on, but even more to the point, you factorize them over exponential families because that's convenient. And then automatic differentiation goes sort of a step further. Automatic differentiation variational inference goes a step further, and it makes this factorization in such a way that essentially you're using Gaussians, everything's Gaussian. This is not the only set of nice distributions. And so there's a body of work that I believe this question is getting at, where they say, hey, you know, here's an alternative nice set of nice distributions. Let's talk about mixtures of Gaussians. And so what's potentially nice about looking at a mixture of Gaussians rather than a single Gaussian is that now you can get multimodality. And so to the extent that you might be doing something where you actually care about multiple modes and you really want to pick them up, that's obviously going to be more useful. The real challenge with that work, and I think in general with getting at anything that's beyond mean field variational Bayes. So we also talked about Turner and Sahani's 2011 paper. They get beyond mean field variational Bayes by getting rid of some of the factorizations. They make like just slightly fewer factorizations. And with all of these things, you have the usual trade-off. Things get slower. So the big reason that we're using any type of variational Bayes is for the speed. And so if you have something that's a bit slower, then you know that's a real trade-off. And then of course you also have these issues of, okay, well, you know, does it work better? Is there something that comes up there? And I think Turner and Sahani's 2011 paper really gets into this very well with this issue of factorization, because it's really unclear. Yes, the KL is lower, but it doesn't mean that you actually get the things you want better, like the mean estimate and the uncertainty estimate. I'll also just briefly address this question because it was on this topic that I was mentioning. Yes, I said sure. We had this paper appearing soon on you know, sort of mixing frequentist and Bayesian ideas of uncertainty, and in particular letting you get sort of frequentist uncertainties with your Bayesian estimates. The first author is my excellent postdoc Ryan Giordano, and the other author is me. So it will be up at some point. I'll put it up on my webpage, but it's not up just yet. Thanks.
And earlier you were mentioning that there are many divergences, not only KL divergence. What about the alpha-beta divergence? It could be possible to adapt the alpha-beta parameters and better tune the target to the peculiarities of the data distribution.
Yeah, honestly, if you can think of any divergence or distance, I am sure you can get something to work. And then the question sort of that arises is it better? And I think that that's really the tricky question, is understanding, you know, is there anything where you can really get a theoretical guarantee? Maybe if you're not focusing on theoretical guarantees, can you really ensure better empirical performance? Why would that be? And I think that's where we just get into a real trickiness. With all of these divergences, is we already have seen some issues with KL divergence. So yes, we can absolutely do other divergences, as we've seen we can do other nice distributions, but what do we get from that? You know, what is the benefit? Is this going to be something that that really performs better, or is it something that performs kind of the same and you know, maybe it's just a bit trickier to deal with and more difficult in practice. Now, that's not to say you shouldn't do it. I think always like pursue these ideas. They're very cool and worth trying out. But it might be that this is the kind of issue that arises when you find yourself, you know, doing experiments and trying to look at theory.
And are there any approaches to balance mass covering mode seeking properties in variational inference?
Are there any approaches to dealing with the mode seeking properties? Is that the
to mass covering and mode seeking? Yeah,
I mean, there's some sense in which, you know, some of the things that we've been talking about already try to address those. So for instance, you know, this idea of having your nice distributions be multimodal, like be a mixture of Gaussians. So then if you don't want a single mode, then you can pick up multiple modes. I do want to emphasize, though, that I think one of the reasons that people really use variational Bayes in the cases that they do is exactly this mode picking out tendency. I want to call it a tendency because it doesn't actually always have to happen, but it certainly often happens. And so it's interesting to think about that. You know, you really have to be I think it's best to start by talking about like, what is your problem? and why do you need something beyond it? Why do you need well, like, what is your actual practical problem with actual practical data? And why do you need something beyond what already is here? Because it might be that there's a different direction. But if you really do somehow have a practical property where, or a practical problem where you really do want to pick out sort of multiple modes, then that could be a way to deal with it. You know, it's also possible to think about alternatives. You know, one thing that's come up a few times is thinking about the KL in the other direction. Now, there's a lot of trickiness to doing that. As I've mentioned before, expectation propagation isn't exactly minimizing the KL in the other direction. There's a lot of other things going on there. But it does have a tendency to average over modes. But again, is that what you want to do? I think when you have multiple modes and you actually care about them, it's probably more that you want to like explain to a practitioner, hey, here are the different things that are going on. You know, like, you know, maybe they really represent different populations. Like maybe you're doing some kind of study for a practitioner on you know, moths. Maybe they're a scientist who studies moths. And if you found that there was some real multimodality in your data, I think what you'd want to do is you'd want to tell them, hey, I found this, and maybe it would turn out to be like 3 different species of moths or something. And so I think usually when there's multimodality, you either have this well, you have one of these 3 types that we talked about before. And so I think it's the same thing in all of these cases where it's like, okay, you know, if you're trying to get away from mass coverage, if you're trying to get away from mode seeking, like what exactly is it that you're trying to say about the distribution? And then you want to think about, you know, what's a method that gets at that.
And how can we leverage variational inference to do research on interpretability?
Okay, so my understanding of the question is, how can we work on variational inference and how does it relate to research on interpretability?
Yes. So if my objective is to do new methods in interpretability, can I use variational inference? And if yes, what could be ideas?
Yeah, I mean, I think interpretability is another one of those big words that encompasses a lot of different things. And so, you know, some notions of interpretability, and I think this is one that I focused on a little bit here, is just this notion that, you know, there are certain things that you want from your problem that are not purely prediction. You know, you want to highlight, hey, I want to learn about some unknown parameter, like, you know, what, for instance, in the microcredit case, you know, maybe I find that actually I really want to look carefully at covariates and I want to understand, is it really meaningful if a particular household has had a business before? Is it really meaningful if a particular household has a certain level of income already? You know, really understanding the effects of different covariates. And so in that case, I think there are ways that you can deal with interpretability that are very simple, like linear models or generalized linear mixed models or things like that. Now, of course, there are other forms of interpretability as we get into things like, you know, vision data and text data and things like that. And I think that those get a little bit farther away from at least the types of things that I've been focusing on here. You know, I think, you know, here we're really talking about parameter estimation and stuff like that. And I think there we're probably getting a little bit farther when we're talking about like explaining something like a convolutional neural net. And from that perspective, I think it's always worth asking yourself too, you know, there's so many tools in the machine learning toolbox. Do you need this particular tool? Sometimes yes, sometimes no. You know, if you're looking at something like a convolutional neural net, you know, it might not be that you need anything strictly Bayesian to deal with that. You know, you can think about interpretability perhaps from the notion of the architecture. I guess this is just like 2 types of interpretability that have come to my mind. I'm sure there are other types and there are other ways that it interacts. I mean, I think if you could take any 2 ideas in machine learning, you can always find some way they interact, but
yes, and now that I mentioned about 2 ideas and how they interact, there is also another related question, and it's on variational inference and normalizing flows. If you see connections and how they interact.
Well, so there's this very nice paper on using normalizing flows for variational inference. So let me just remind myself of the exact title. So it's this paper by Resende and Mohammed, Variational Inference with Normalizing Flows, and you know, it's been a very influential paper. I think this is again, you know, thinking about better ways to do variational inference. You know, are there things that we could do that are more flexible? And so it's certainly an interesting idea. I am sure that this is not the only connection to normalizing flows. Like I think there have been so many other ones, but this is the one that immediately comes to mind. And I think it's probably cool if you haven't already read that paper.
And if we want to estimate deep Bayesian networks, Will using Markov chain Monte Carlo make sense?
Yeah, so okay, so this I think this question about using any of these methods for deep Bayesian networks comes back to my somehow a few of my other discussions. I think there's a real question with deep Bayesian networks about what exactly is it that you're doing. And I think I'm not convinced that what you are doing is trying to actually look at the exact posterior in a deep Bayesian network. Like I don't think anybody's trying to get all of the. I think that's a case where we have a huge number of modes. I don't think people tend to look at all of the modes or feel like they're all meaningful and something that they want to do. And so I think there it's at least for me, it still remains to be seen. Like what exactly is the goal, and does it really involve the full posterior or just some aspect of the posterior, or like what are we trying to do there? Certainly, I will say I do not expect either Markov chain Monte Carlo or variational Bayes to fully explore that posterior. I mean, one of the points that I've been making again and again is that every method of machine learning has pros and cons, and Markov chain Monte Carlo is no exception to that. It is not perfect, just as there is no method in machine learning that is perfect. And some of the challenges of Markov chain Monte Carlo include being able, and this is sort of a fundamental challenge in exploring any distribution. I don't think this is specific to Markov chain Monte Carlo. I don't think it's specific to variational Bayes. If you fundamentally have a ton of modes, it is just really hard to find those different modes. You get into above 2 dimensions, and how do you even know another mode exists when fundamentally you're dealing with unnormalized distributions, so you don't even know that there's more mass? And then how could you possibly find it? You can't explore anything in 3 dimensions or more, really, and often you're dealing with many more dimensions than that. So you have all these modes. There's definitely no method, I think even any method that you could come up with would not explore them unless you knew somehow where they were. I mean, if you had some additional information about where they were, maybe you could hope to explore them. But even if you could explore them all, like, is that meaningful? Do you really need to do something with that? I think these are the types of questions that need to be answered before it's clear, before we can drill down into like Markov chain Monte Carlo versus variational Bayes.
Yes, and well, you even mentioned that there are so many methods, and not everything makes sense, and so on. So, the progress is in general very fast in this space. So, how many papers should we read per week to keep up with the new trends?
Yeah, this is great. I mean, it's impossible, right? Like, there's too many papers that are out there. There's no way. I mean, I honestly feel pretty strongly that, and I've kind of mentioned this already, that there's just a lot of really great foundational stuff out there. And I think it's such a better use of your time to really understand the foundations than it is to try to keep up with the absolute latest, papers. Once you really grasp the fundamental ideas that are motivating everything and the fundamental tool sets that are going into everything, and I don't think that those have changed dramatically over time. I mean, obviously, the huge exception to this is deep learning. I do think that deep learning in particular is something that has really arisen as a relatively new tool. But I mean, even it has its underpinnings in neural nets, which are around much longer. And so I think if you had some understanding of that, you could easily jump into some of that literature. And honestly, even some of the ideas in deep learning were certainly around before that. They just weren't as practical. But I think in all of these cases, if you have a really strong foundation, then you're much better able to read papers too. So something that I do in one of my classes that I teach is we go through and we read papers. And I think there's a real art to reading papers. It's easy to get caught in this cycle of sort of just reading an abstract and then taking that as gospel, that everything that says is exactly right. When the reality is that like you really have to dig in to see like what are the authors not saying, how does this relate to other things, what's missing here, what's not being done, how many assumptions are being made that may or may not be realistic. And so I think from that perspective, really spending your time on foundational work gets you better prepared to ask those questions. And better prepared to understand, what's really going on in papers and research. So that would be my thought.
Yes, and besides reading foundational literature and learning how to read papers, which other suggestions do you have for researchers who have just started in machine learning?
Oh, it's an interesting question. So I here's this is all my personal opinion. Obviously, people can have different opinions, so take it with a grain of salt. But I personally see machine learning as a service discipline. Like our job is to make other people's data analyses be fast and accurate and to get like the information that they need from them. So I think that we're supporting science, we're supporting engineering, We're supporting, even vision and NLP. I think of as like, these are the places that actually have the data sets and are generating the data sets and are analyzing the data sets, but also the social sciences. And so I think like the best thing that you can do is to spend time really understanding an applied problem, because it's the applied problem that really matters, right? Like you can do all kinds of crazy things within machine learning, and then I think it's surprisingly easy to do something that you think is like crazy general and applies to everything, and actually in the end applies to nothing. I think it's much better to have a single, clear, motivating example of something where you really care about the end goal, the data analysis goal at the end, rather than trying to make things so very general. Because it's not always clear that there's at least a single example. And so I think just really focusing on an applied problem and understanding that applied problem and understanding, what is needed for that, and what benefits could be there is very motivating for new machine learning research. Because I just think for any like sort of non-trivial applied problem, if you try out all of the methods that already exist, or like at least your best stab at it, there's going to be something that's like not quite fitting, and they're going to want something else from the practitioner's perspective, and then that's an opportunity for research.
And as a last question, could you please share with us, how did you get started in machine learning? What brought you to the field?
Oh yeah, so I got into machine learning before it was cool to be in machine learning. So when I was in undergraduate, I really liked math, and I really liked physics, and I really liked computer science. And I was like, man, it's too bad these things don't intersect somehow. And so towards the end of my undergraduate time, I took, it turned out our university had like one machine learning course, and it was very sparsely attended, which is very different now. And I was like, oh, this is pretty cool. I'd like to do something like this. I really in particular, I really liked measure theory when I was doing math, and I went to the undergrad advisor, and I was like, oh, could I do measure theory, for my research, like in life? Like, I'd really like to do some kind of research. And he was like, no, it's dead, but you should check out probability theory. And I was like, okay, cool, I'll do that. And I was doing astrophysics research. So my first research was in astrophysics, understanding things like dark matter and dark energy, and the Sloan Digital Sky Survey was new at the time. And so you could really get some like really interesting sort of statistical sense of what dark matter looked like. And from supernovae standard candles, you could get some sense of like what dark energy behaved like. And so we were doing basically all this data analysis, like we were doing, like Markov chain Monte Carlo. And I remember at the time thinking, gosh, I wish I had a better understanding of these tools, because they're clearly making assumptions. And I worry a little bit, like, am I making the right assumptions? Am I using them the right way? And so for me, coming out of undergrad, I was like, man, I don't know what to do with my life at all. Like, I like all these different things. And so what really worked out well for me was I ended up spending 2 years in the United Kingdom on one of these like Bring Americans to England scholarships. And it was there that I discovered, it was like, oh, wow, all of my interests coalesce exactly in basically Bayesian inference. It was like, oh, the probability comes into Bayesian inference. All the stuff we were doing in astrophysics for applications, that was Bayesian inference. The machine learning is like, oh, this is a type of machine learning, this is a type of data analysis. And I think one thing that's really been super exciting to me about machine learning in general and Bayesian inference in particular is just this exact wedding of beautiful math, like the potential to do all this like super fun math, but to have it be really applicable and to have it matter, and to have it be something that you can really apply. And I think that just makes this like this perfect field where, what you're doing really matters, it has real impact, but you also get to do all this super fun math along the way. So it's just really nice like that. And so anyway, I started doing some research on Bayesian inference with, at the time, Bobby Gramercy and David Mackay, who were both
super
awesome to let me work in their labs. And I thought, oh wow, this is exactly what I want to do. And so then I applied to do my PhD with Michael Jordan, and I worked with him for a bit. And I just feel like it was a really great experience for me to have some time to sort of figure out like, what really appealed to me. And I think what's really cool about this too is it was an area where I felt like, oh, hopefully I'll innovate and I'll do something, but if nothing else, I'll have this super useful skill set. And I think that's what really matters, is having this ability to, there's still so many people who find it so useful for you to collaborate with them, to analyze their data, to do something really useful with their data. And I think that's what's, just super exciting about this area.
Well, thank you very much, Tamara. This has been fantastic 4 days. We have learned so much, and I am sure the participants will be writing you. There were so many questions, we were not able to address them all. And we will be definitely looking more into variational inference methods. They are definitely very general. They can be used to almost every problem, and we should all be using them.
I think there's like a great toolbox of methods, and this is one of many. So it's great stuff. Thank you so much. It's been a real pleasure. I appreciate all the like fantastic questions and engagement throughout the multiple days. So big thanks to everybody, and thanks to the organizers. This is has been really amazing, and I think it's been a real challenge putting everything online, but my experience has been very smooth and good. So big thanks.
We're happy to hear that. Well.